Okay, so the session is being recorded now, including the chat. Our topic for this week in practical is the reflection and refraction of light. So basically we will, let me switch on my camera. Basically what we will do is we will keep WhatsApp with you. We will study the behavior of light depend on the environment where it is. First, when light hits a shiny surface, it gets reflected. So what will be the behavior of light during reflection? Reflection can happen if the surface is flat or plane, okay, that's called a plane surface, or if the surface is curved. And then later on, we will study refraction, that's the bending of light when it travels to two different media, or medium of transmission. So when we say medium, it's a material where light is passing through, transparent objects, okay? And by measuring the refraction of light inside the medium, we will calculate or determine the index of refraction of the medium. Now, instead of acrylic, you can remove acrylic here, okay? In your report, if I ask you to remove acrylic, then you should not write acrylic. Instead, we will use gazaz. So instead of index of refraction of acrylic trapezoid, we will use a glass trapezoid. Okay? The same here. We will study what we call total internal reflection, which happens inside a glass trapezoid. So what's the difference between them? The material. The material we use is glass instead of acrylic. In physics lab, we have acrylic trapezoid, but here we will use simulation, and the simulation will be using glass trapezoid, okay? And then finally, we will study what we call thin lenses, okay? So when we talk about thin lenses, we are talking about convex lens, and I will teach you by simulation how to find the focal length of a convex lens. So let's begin. Because this is actually a little bit long, we are going to make 5 tables, okay? Let's start with reflection. Reflection happens because when light is traveling in air or even in vacuum, basically when light travels, okay, and it hits a shiny surface, now we can say that the light is traveling in a straight line, okay? That light traveling in a straight line, we call it a light ray, okay? When it hits a shiny surface, what happens is that, let's zoom into this image here. When the light ray travels and hits a shiny surface, we call that shiny surface mirror, okay? That light is called incident ray. It makes an angle with the mirror, and then when it's reflected, it is called now a reflected ray. And again, the reflected ray also makes an angle with the mirror. And we will find the relationship between the incident ray and the reflected ray, or the incident angle, this one here. Whoa, what happened to my pen? I have to replace the battery now. The incident angle and the reflected angle. What's the relationship between them? And these two are being measured from a line which we call normal. So what is a normal line? This line, it's an imaginary line which is 90 degrees from the surface of the mirror, okay? So how do we do that? I will send you a simulation, which is, where's my simulation? I already have it opened. Oh, here. I will send you a simulation, which is this one, okay? So I'll copy the link, and I will go to Blackboard. I'll go to chat, and I will send you the link to the simulation, and I want you to open it. Open the link to the simulation, okay? And you can click intro there. So here, yeah, it is web. It is a browser. Okay, if you want, I can send it also to the group chat in Telegram. So that's the simulation, okay? So here you have a laser light or a source of light, switch on and off, okay? You can change the angle from 0 degrees to 90 degrees. And this is the normal line, Okay, now the object you have at the top is air and at the bottom is water. We can change it to glass instead. Okay, now when you change the angle like this with the light on, let's start from 0. The light is being reflected from the surface. Some of the light will pass through, okay, because this is not completely opaque. It's actually a transparent glass, okay. And if you change the angle of the incident here, okay, by moving, you can see that the reflected light here also changes. And what we want, if we go back to the data sheet, is to measure theta I incident and theta I prime, which is reflected, okay, and find the relationship. So what you will do is go to table 1, okay, table 1A, and then fill the table. So let's start with S number 1 reading, second reading, and third reading. What are the angles that we are going to measure? So we can measure 30, 45, and 60-degree angle, okay? So let's go to our simulation, and I want you to make the angles 30, 45, and 60. So how do you make those angles? You take the degree scale, okay, and make alignment with 0 on the normal line, and 90 on the surface of the mirror, okay? So 90 on the surface of the mirror and 0 on the normal line there. And from here, just shine the light at 30, 45, and 60, okay? And then you take the reading of the, let's say for example, I will use 10 degrees or 20 degrees, okay? For example only, I will use 20 degrees. And then take a reading. So how will you take a reading from here and how will you submit the report? I want you to take a screenshot, okay? You can take screenshot from here. You see the bottom? Screenshot. Just click it and there's the screenshot, okay? Now, if you want, you can actually edit the screenshot or just close that one. Let me just take another screenshot, okay? Or you can draw on it also. Edit and draw, okay? What are the angles that you will read? Angle number 1, what's the angle here? Angle number 2, what's the angle here? That angle is theta prime, theta 1 and theta 1 prime, okay? Once you have your angles, you can write it on the figure if you want. Save your screenshot and you can submit it in your report. So which angles are you going to choose? 30, 40, and 60. Is that clear, Shabab? So you just put the answers here. Clear? Answer, please, so that
like
I know.
30 degree angle 30. What it is in the diagram, right?
Yes. What is the angle that is reflected? Okay. So the angle that is provided incident is this one. The reflected angle is this one. What are these two angles? So 30. What's the reflected? Honestly, if you are listening to me, you can see the answer right now. 45. Okay, and 60. Wallah, if you want to change the angle, sure, you can go from 0 to 89. Why? Because if it's 90, the light will not be reflected on the surface. It will be parallel to the surface. You can have 85, 80, 75, 70, 65, 60, whichever. I will suggest, to make it easy for you, 30, 45, and 60. Okay?
Same.
Done. You can have 10 if you want, sure, 10. Okay?
No, same.
10,
I mean
20,
same.
30.
30, 45, 60.
Yeah, let them decide if it's the same or not the same. Okay? But I want to see at least one screenshot to submit in your report. Clear? Shabab, clear?
Yes.
Okay, let's go to table 2. As I said, 5 tables, so we have to go fast so that we will not use too much of the time. Because remember, we have only 3 periods. Okay? Well, it's enough. In the lab, it's enough. So in table 2, we will study the reflection in a cylindrical mirror. So what is a cylindrical mirror? The mirror reflection we are doing in table 1 is a plane mirror or flat. A cylindrical mirror is a mirror that is curved, okay? And the curve can come in two directions, concave and convex. So when we say concave, let's say the light is coming from the left, like this. So that's the light, or the direction of the light. The mirror reflecting is on the inside of the curve, okay? You can remember it by saying wadi, concave mirror. So let's say that's the mirror. What about convex mirror? It's the opposite. So the light is still coming from the left, going to the right. A convex mirror is like jebel, like this. Okay? The reflecting side is on the outside of the curve. So that's the idea about the convex and the concave mirror. So the question is, how do we find the focal length of the cylindrical mirrors? And what is focal length anyway? Well, from the word itself, focal length is where a mirror will focus an image or a light, okay? And you can see that by, in the lab, we turn off the light. We have a light source, which is parallel lights, and we shine the light source on our mirror, okay? And you will see something like this. So as you can see, the shiny side, it's a concave mirror. The parallel light's coming from the left, and the light will be shined, okay? The light will be shined at a point. There. I don't know if you see it. Let me replay. There, okay? So the light will be parallel from the source, but once it strikes the mirror, the light will be reflected at each point, okay? So here, the reflection point of this line, at this point, the reflection will still be equal to the incident ray. At this point in the middle, the reflected ray will be equal to the incident ray angle, okay? And at point 3, it will also be equal. But the reflected light will not be parallel because the mirror itself is curved, okay? When you have a curved mirror, it will focus a light together at a point, and when this focus will appear in front of the mirror, this is the mirror, so in front of the mirror here, this is called a converging mirror. So it will converge the light at one point. Is that clear? And that point is the focal point of the mirror. Once you have the focal point of the mirror, you can measure the distance from the mirror surface to that point, and that's called the focal length. Now in the lab, you will trace the line of the light ray. You have to place points where the light is passing through, on the surface of the mirror where it's bouncing, and on the focal point. And then we draw a pencil line, a very thin line, to indicate the focal point. Okay, so how do we do that? I have the drawing already with me, and I will send the drawing to you. Okay, so we are using table 1B. I will go to my notes, and I will show you the drawing of table 1B. There. Okay, so that's table 1B. And this is the drawing for the concave mirror. I have the mirror on the left. I have the light coming from the right. So if we trace the light, it will move in this direction, strike the mirror, and then bounce in this direction until all the light will meet at one point, which is called the focal point. Okay? So what is the focal length in table 1B? The focal length will be the distance from the surface of the mirror here, okay, up to the focal point. That's the focal length. So what you will do simply is you will take the image, okay, 1 second, I will open the image and send it on your group chat. Nope, not that one. Okay, so you will download the image if you want to print as you like, but you can actually read. Even from now, you can read it from my screen. Don't put it in the type. Don't type it in the chat, okay? No need. Just anybody can read from his own, okay? What is the focal length at point F? You have the mascara already here. So just take the reading here, okay? Now, what do we do in physics lab once we have the focal point? We take what we call a drawing compass. You know what's a drawing compass? It's used to make circles, okay? I have a picture. If you want to see a picture of a drawing compass, this one here, this one. So what do we do with this device? We actually take this device. Now, in most situations, okay, this device has a pencil and a pin. The legs of the compass has a pencil and a pin. This is the pin, and this is the pencil, okay? We take the drawing compass, and then we place the pin. Let me get my pen. Okay, pen. Let me use a different color. Okay, we place the pin of the compass at point F, okay? And we open the legs and point the pencil at the surface of the mirror. So your compass will be open like this, okay? Across the focal length. And then what we do is we swing the compass to the opposite side until it will make a line across the center, okay? This line is a line of 2F, okay? So you get the idea how we get 2F in this figure? So you swing the compass around and you get the point 2F. What's the idea about the point 2F? The point that is 2F is basically the same as the focal length from F. So this is twice the focal length, okay? And if you combine the focal length and the 2F, your 2F is actually going to be equal to R. What is R? That's the radius of curvature of the mirror. What do we mean radius of curvature of a mirror? Well, a radius comes from a circle, okay? Let's say we have this circle. And let me adjust the size of the circle because this is too small. Come on, circle. There you go. Let me make the circle bigger, okay? There. Now, when we say radius, we know that we are talking about the center of the circle approximately here, okay? So that point is the radius of my circle. That's the distance from the circle up to the center of your circle, radius. 1 second, Shabab. Sorry about that. So anyway, you have your circle, you have your radius. What do we mean radius of curvature? If you take a line, okay, and cut our circle like this, okay, so now we cut our circle. What's gonna happen? Let's remove the part of the circle where we cut it. Okay, I will use white to erase the part of the circle which we cut. So this will take some time because I cannot erase the circle completely. I just need to erase the part which I cut it. Well, I wish I made the circle smaller. Erase, 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 erase. Okay. Good thing my pen is working now. Erase it. Okay, now I have erased the part of the circle which is cut. I will now erase the line. Okay, erase this line here. And then in my drawing, I'm going to remove the grid. You know, the graph paper, just white. There. So what do we notice here? What we have, Shabab, is like the shape of our mirror. Okay, let's go to our mirror. Let's look at the shape. Oh, wait. Where's my drawing? Let's look at the shape of our mirror. There. So if you can see, the curve of this mirror is actually like a part of a circle like this, where the focal point is here, okay? And the radius of curvature is here. And the radius of curvature is equal to double of your f. Is that clear, Shabab? This is actually the mirror. So if we shine the light, let me make my lines bigger. If we shine the light like this, it will bounce off the mirror and it will go to the focus. If we shine a light here, it will bounce from the mirror and it will go to the focus. So at any point where you shine the light, it will bounce from the focus and it will from the mirror and it will go to the focal point. If you double that focal point, it will become the radius of that circle. Well, what circle are we talking about? Let's erase the white. That circle there. Okay, so a curved mirror, convex or concave, is actually part of a complete circle, assuming that your circle is, of course, or your mirror is perfect. Any questions, Shabab? Any questions? Okay, so that's how you will fill the information in this table. So I gave you already the graph for the, let me erase all of these things. I gave you all the graph or the drawing. You don't need to draw this one. In the lab, if we are doing this in GIC lab, you have to do this drawing by yourself, okay? So this is concave mirror for table 1B, and this is the convex mirror for table 1B. So how does the convex mirror work? Let's go and watch the video of how a convex mirror works. So you see, a convex mirror, the shiny side is on the outside of the curve. Can you see that? The shiny side is on the outside of the curve. So what happens when it's struck by parallel lines? There you go. So what happens? The light, okay, will actually separate. Instead of putting them together, the light will be separated and they will go away from each other because of the curvature of the mirror. So the problem here is that how do you make the lines focus? Okay? How do you, if you continue this line and this line and this line, they will not meet because they are diverging. That's why this is called a diverging mirror. So how do you make them focus? Well, let's close this one now. And let's go back to the drawing. The technique is that the image will actually focus behind the mirror. That's why it will be a virtual image, okay? So how do we do that? Simple, just trace the lines. Yes, they will meet on the inside of the mirror. This is the original, this is the reflected, this is the reflected, okay? This is the incident ray, this is the incident ray. Once you have the reflection point, just trace the light ray and then make extension. Oops, sorry. Make extension going behind or inside the mirror, okay? And you will see that these lines will meet at a certain point, even the one in the center here. At a certain point, that's the focal point. Again, measure by mascara, that's the focal length. Okay, and of course using a compass with the 2F, this is the radius of curvature. In fact, if you take a compass, put the pin here and put the pencil here, you will actually make the complete shape of the circle following the shape of the mirror. That's how the mirror, the curved mirror works, okay? So table 1B is actually easy to fill. You have this reading, you have this image, I just sent it to you. You just need to read from the mastera which is included in this image. If you want to study it again, the session is recorded and once it's uploaded, then you can study again how to read, okay? Let's go to the next part. If there is no more questions, we can go now to table 2 because table 2, especially table 3, will take a long time to explain. Any questions? Shabab, any questions? Come on, my throat is getting
No.
dry from all the talking. Okay. So how does refraction work? Okay. Well, refraction is a phenomenon where light traveling through any transparent material, light that's traveling through any transparent material, we call medium. Okay. If light can travel through the material, we call it a medium of light, including vacuum, because vacuum in space, light can travel. That's how the light from the sun and the stars will actually reach the Earth, okay? So including vacuum, that's a medium of light. Now, when light travels in a vacuum, without the effect of gravity, the light will travel in a straight line, in a perfectly straight line. However, because light behaves as a wave, okay? Light behaves as a wave as well as a particle anyway. When the light travels to two medium, okay, we call two medium, and this two medium has what we call a different index of refraction. The idea is that at the boundary of the two medium, the light will bend. And when the light is bent, we say that it is refracted, okay? Why is the light refracted, or why is the direction of the light changing? That's because the medium or the material where light is traveling through is affecting what we call the speed of light. Okay, and this effect is called the index of refraction. Okay, the speed of light in vacuum is approximately 300,000 kilometers per second. That's how fast light is traveling. Between the sun and the earth is about 180 million kilometers. The light coming from the sun will reach the earth in only 8 minutes. That's how fast light travels, okay? So the idea is that in vacuum, because there is no material, it's empty, light will travel at 300,000 kilometers per second. But if you take this light and make it travel in a transparent material like acrylic. What else? I have here glass, and what's inside the glass? Water. What else? Any transparent, that is any material that's transparent where light can pass through, okay, is a medium of light. The speed of light will slow down. So the speed of light in that material will not be equal to c, because c is 300,000 kilometers per second. It's actually 290 something, okay? So inside the material, the speed of light will change. It will slow down. And because of this change in speed, the direction of the light will change. And I have one image here which shows it actually very nicely. Here, okay? In this image, you can see the light is traveling in air. The light is traveling in air, okay? So let me write the material here. This one is air, okay? And then once it travels inside the glass, it will bend, okay? And then once it goes through the glass in the boundary, again, it will travel to air, so it will bend again. Whenever light travels to two different material, it will bend at the boundary. Why is that? Because the speed of light changes, okay? What affects the speed of light is what we call the index of refraction. Index of refraction is n. Now, because we have two materials, in refraction, the material 1, where the light is coming from, that's n1. Material 2, where the light will bend, okay, in this case glass, that's n2. And then it goes back to material 1, so n1. We have two indices of refraction, and we need to determine the index of refraction of glass. That's the objective of this experiment, okay? Well, in order to do that, which equation are we going to use? We will use what we call Snell's law. Snell's law tells us that, this rule, this should be in your theory, When light is traveling across the boundary of two transparent material, in this case air and glass, okay, the index of refraction of air, N1, the index of refraction of glass, N2, is given by this equation. So we need to measure the angle θ1 and the angle θ2. So how do we determine the angle θ1 and the angle θ2? Let's go back to our note, okay? Where are the angles here? Well, the angle is actually found from the normal, okay? Just like in reflection, there is a normal line in refraction. In this case, this is the normal. The normal line must be 90 degrees with the surface of the, excuse me, let me just get my pen. Okay, the normal line must be 90 degrees with the surface of the parallel lines where the light is striking. So this is the parallel line. That's 90 degrees where the light is striking. Okay, let me just make it look more 90 degrees. Something like this. And of course, the light must hit at this point at the normal. So where's the angle θ1 and θ2? Because air is your N1, the angle with the normal of the light in air is your θ1. And glass is N2, the angle of the light inside the glass, that's θ2. And this line is your normal. Any questions, Shabab? So how do you find the value of N2 and the value of N1? Let me write it here, the equation. Nope, let's go to the white part. N1 sine θ1 is equal to N2 sine θ2. Okay, that's the rule for Snell's law. So the question is, we know θ1. We can also measure θ2. What is N1 and what is N2? One of them must be given, okay? In vacuum, the N for vacuum is equal to 1. Okay? The N for air is also equal to 1, but with a slight difference, 1.0003. So there is a very small difference. But because of this small difference, in the atmosphere of the Earth, light from the sun will actually bend in the atmosphere of the Earth. Okay? It will also bend in the atmosphere of the Earth. That is why sometimes when the sun will go up or the sun will go down, the color of the sun is different as opposed to when the sun is straight up in the sky. Okay? That's because of the bending of the light in the atmosphere of the Earth. But for this experiment, because we are using a small glass and, not as big as the size of the Earth, we can use the value for air N1 as equal to 1 to simplify the calculations. Okay? So let's take the value N1 is equal to 1. Let's remove this so you don't get confused. Let's remove that line. Okay, now that you have the value of N1, how do you calculate the value of N2? This is how you calculate it. First, divide both sides of the equation by sine θ2. This will cancel. This will cancel. You will be left with N2 is equal to what? N1 sine θ1 over sine θ2. Is that clear? So what you need to know to get now is the angle of θ1 and θ2. So how do you get the angle of excuse me, θ1 and θ2? Go back to the simulation. Remember the simulation that I gave you in the link? Okay. Instead of intro, go to Prism down here. Or if you want to see it again, let's go to Home. Instead of intro, go to Prism. Okay. Once you have the prism, you will get it like this. You can select the dark screen, or you can go with the light screen as you like, as long as when you switch on the light, you can see the line, okay? Take the prism, which is a trapezoid. The trapezoid has two sides parallel, and two sides are not parallel, okay? You have to shine the light on the parallel sides of the trapezoid. So you can rotate the trapezoid until you get the refraction here, okay? You can see there, now I have the refracted light. You can change the material, water, air, or glass. You know, if it's air here and it's air inside, the light will just pass through. Why? Because the index of refraction is the same. But if the index of refraction of the two materials are different, the light will bend, okay? Let's shine it on the parallel side. There you go. The light will bend depending on the different index of refraction, okay? So in this case, we are using glass. So make it so that the light will bend like this. But then, you want to take the protractor and measure the angle theta 1 and theta 2. So where is theta 1 and theta 2 again? That's theta 1, and this is theta 2. And remember that you have to measure from the normal. The normal is 90 degrees to the surface of the boundary, okay? So here you can easily find the normal. Just click normal, and there's the normal line, okay? Get the degree scale, like this. Rotate the degree scale so that, rotate the degree scale so that the 0 will be with the normal. Okay, like this. So the 0 with the normal. What else? You have to make sure that the 90 is with the surface of the glass, of the prism. Okay? And then, once you have your alignment perfect, you have to make sure that the degree scale is aligned perfectly. There, okay? You can adjust your angles a little bit if you want, as long as you are within the shape of the prism. Okay, you can adjust the angle as you want, as long as you are within the shape of the prism, and do not lose the alignment of your degree scale. Okay, there. Once your degree scale is aligned, you can take screenshot. Okay, once you have the screenshot, you can open it, and now we can zoom in. You see why it's important to get the screenshot? Because once you zoom in, you can check if your alignment is perfect. You can see now my 0 is not perfectly aligned. Okay, I can go back to my simulation. Where's my simulation? Okay, close this one, and I can adjust my angle a little bit, and again take a screenshot. Okay, open the screenshot, and when you zoom in, now you can see that your alignment is much better. Okay, so it's up to you. Just make sure that you have very good alignment. What's next? You have to read the angles. Okay, I will go to edit and draw on this figure. Now, when you draw on the figure, you can see that it's actually become small again. So there is another technique for a screenshot where you can draw on the figure easily. Okay, take a screenshot like this using the snipping tool, or if you want, you can only focus on the angles here. Once you have the screenshot, you can see this one, this is my screenshot, you can save it and then you can edit. Okay, or you can edit with Paint from here, or you can edit with another software. In my case, I will go to OneNote. Okay, you can see that I already have one image. This is from my previous class. They want to choose the dark screen. Okay, I can I can paste my my image here, and I can zoom in manually like this. Okay, so you can use the image to zoom in, and now I can draw on my angles. So the question here now, Shabab, where is theta 1 and where is theta 2? From the normal line, that's theta 1. From the normal line here, that's theta 2. Is that clear? What is theta 1? From 0, what is this angle? What is theta 2? From 0, what is this angle? Take the reading and then record theta 1 and theta 2. Theta 1 is the incident, theta 2 is the refracted. Once you've recorded it, go to your data sheet, okay? Table number 2, angle of incidence, theta 1. Angle of refraction, theta 2. Forget about this one. Just one reading is enough, okay? One reading is enough. Calculated index of refraction, change the material. Instead of acrylic, we are using glass, okay? What is N1? Just so you will remember, it's air. It's equal to 1. Index of refraction of glass, it is N2. How do we find N2? As we go back to the notes which I write, N2 is given by this equation. N1 sine theta 1 over sine theta 2. So this one sine theta 2. Okay, so N1 sine theta 1 over sine theta 2. Once you do this calculation, you can write the answer. N2 is equal to this. Any questions? Any questions, guys? Okay, good. You know, in the lab, you have to make the drawing. What drawing? You will make this simulation, okay? You will make this with the actual source of light, and you will make this simulation with mascara, with the prism, and you will draw the path of the light and the curve, and then later you will measure the angles. So it's actually beautiful in the lab, but what can we do? This is not given in the final exam because you cannot have this in, you cannot have the exam in a dark room, okay? Now, let's continue. Once you've done, no need to make average because you are only make one reading, okay? Once you're done with refraction, it's time to go to total internal reflection. What is total internal reflection? Well, let's go to the simulation and I will show you what is total internal reflection, okay? Let's reset this one. I want to make it in a dark screen like this. Again, I will take my prism, okay? I will show the light like this. And as you can see, it's still refraction. By the way, you can move the light anywhere. You can rotate it 360 degrees, okay? You can bring the prism anywhere, and you can also rotate it in 360 degrees. And this is important for our experiment, which is total internal reflection. Why? Let's start with refraction, okay? This is refraction. Bending the light. This one is already clear, okay? This one is already clear, bending the light. Now, what happens if we continue to rotate the prism and shine it on the other side, okay? Let's say that we shine the prism like this, okay? You will see that in the prism, it actually splits the light into different colors at the opposite side of the prism. Can you see the different colors here at the bottom of the screen? Can you see the different color of light? There, that's the rainbow, okay? Actually, that's what happens when light from the sun will hit the water in the air, okay? Because the water has a higher index of refraction compared to air. When the light from the sun hits the water crystal in the air, it will make a rainbow in the sky. That's how it works. And even the atmosphere of the sun will make a rainbow in the sky, but you don't see the rainbow with all the colors. We can only see part of the colors. What do we mean by that? As the sun is, because of the rotation of the earth, as the sun is setting, okay, one by one, the color will disappear from the original color of the sun. The original color of the light from the sun is, of course, white. Okay? And the first color that will disappear is blue. You see? Why? Because it will be reflected internally. Okay? The last color that you see is, tell me what's the last color that you will see as I rotate the prism. Turkey is very fast. How did you know it's going to be red? There. Why? And how do we know that it's red? The first color that you will notice when the sun is going down is yellow. And then the sky at Maghrib will become orange. And when the sun is really down and say there is no clouds, it's a very clear sky, you will see the last color is red, okay, before the sun will completely disappear. After Maghrib, the light will not be black. The sky will not be black. No, it will still be yellow, but then orange, but then red. That's because the frequency of red is less than green and less than blue. Okay? So the prism, because of the refraction of light, will actually affect the speed of light depending on the frequency. The light with the biggest frequency is, it's actually biggest wavelength is red. Okay, it has the least frequency, so it will be the last color that will disappear. After, okay, after the color has disappeared, all the light, as you can see, will be reflected internally inside the prism. All the light will be reflected inside the prism, and this phenomenon, or this observation, is what we call total internal reflection. Okay, is that clear, Shawab, what it means, total internal reflection? When all the light inside the glass is reflected and none of the light is refracted. Is that clear, Shawab, what it means, total internal reflection? Hello? Hello? The white will actually separate in more than three. The visible light will separate from red, orange, yellow, green, blue, violet, and there's one other light between blue and violet. Okay? So total internal reflection happens when all the light is reflected inside a prism. Okay, let me just try and get it again. And it happens because of what we call a critical angle. Okay, so what does it mean, critical angle? One second. Let me try and get a clear angle. There. So the critical angle happens when all the light, the angle inside the prism, when all the light is reflected internally. Okay? Let me take a screenshot here and show you where is the critical angle. So the critical angle is actually this angle here. The critical angle, we cannot see it with the dark screen. Let's do it with the light screen. Okay, screenshot. Open the screenshot, make drawing. Okay, the critical angle is this here. Okay, but it's not directly the critical angle. It's actually 1/2 or double the critical angle. So what we will do, we will measure this angle, and this angle is double the critical angle. Always remember that there is a normal line that will cut or divide the angle by 2. Okay, so how do we find the critical angle? The critical angle is the angle where the reflection will happen. Okay? Now, at the point where the reflection will happen, there is a boundary of material. Outside, there is air. Inside, there is glass. Whichever of these two material has more density, okay, more density, that is our N1. Whichever of these two material has less density, that's our N2. In order to calculate the critical angle, we again use the Snell's law. What's the Snell's law? Sine of the critical angle is equal to N2 over N1. What do you notice, Shabab? In total internal reflection, air is N2. In refraction, air is N1. So don't get confused, okay? So we will go back to our data sheet and we will find the critical angle two ways. By experiment, number one, and number two, by calculation using Snell's law. So by experiment, go to your simulation, okay? Make your total internal reflection like this. Make a screenshot with, okay, so that's the normal, okay? Make a screenshot with your degree scale. What do you do with the degree scale? You place the degree scale here and make or measure your angle between the two lines, okay? 1 second. There, okay? You have to read this angle, okay? How do you read this angle? You know, you can also zoom in your blackboard. Do you know how to zoom in your blackboard, Shabab? So for me, I'm zoomed in my blackboard. I will take a screenshot so that you can see how to zoom in your blackboard if you're not familiar. So in your blackboard, okay, again, 1 second. There. Now I will zoom out. In your blackboard, you can see the buttons here. That's for zooming in the upper left of your screen, okay? So here, this is our 0. We want to read this angle. That angle is equal to double of the critical angle, 2 theta c, okay? So how do you read it? How do you read it? How much is this angle? Anyone? This is 0, okay? This is 10. This is 20, 30, 40, 50, 60, 70. How much is the angle? This is 65. It's not exactly 65, between 65 and 70. So it's around 60, maybe 68, okay? Let's say 68. So double of theta c is equal to, again, let me write it properly. Double of theta c is equal to 68 degrees. Go back to your data sheet. Write it here. Double of theta c, 68 degrees. How do you get theta c from this number? Divide by 2. So what is 68 divided by 2? 34. Okay, simple. Next, substitute critical angle by Snell's law. The rule, sine of the critical angle equals N2 over N1. What is N2 again? Okay, what is N2? In total internal reflection, N2 is air. It's equal to 1. What is N1? Gazaz or glass. It's equal to, oh wait, we don't know what it's equal to. Okay, but if you go back to table 2, what's important with, oh my god, what did I just do? I messed up my, there. If you go back to table, it's just crashed. Let me just open it again. And I just lost all my notes. Okay, I'm back with my data sheet. I hope that the notes are still there. Yes, the notes are still there. See? Let's go to the data sheet. Okay, some of the notes are still there. So again, what's the rule here? Sine, let's write it again. Sine theta c is equal to n2 over n1. We know that n2 is air, so that's 1. Over, what is n1? Go back to table 2, okay, and substitute the value for glass here. Always remember that the value of n is always bigger than or equal to 1, okay? N for vacuum is 1. Any material which is not vacuum should be bigger than 1. Any questions, Shabab? You will get the index of refraction of glass from table 2 and substitute it as N1 for table 3, okay? Any questions? Shabab, any questions? What about the others? Okay, let's continue. You see, we can finish it in a little bit more than 1 hour. We are just reaching 1 hour now. What is a convex lens? We already showed you what is a convex mirror and a concave mirror. So what is a convex lens? The best example of a convex lens are actually the lens of your eyes. Okay? What else? The lens if you are wearing glasses. What else? The lens that you use for the camera of your phone, of your mobile phone. Those are convex lenses. There is also a concave lens. Okay? Let me show you the two different lenses, convex and concave. This is a convex lens, and this is a concave lens. But these are plano concave, they have a flat side, okay, because we use them on the table. What about lenses that we use in, we don't need this one now, lenses that we use in real life, okay, like the ones from the glasses. I have also the image for some lenses here. So these are also lenses, okay, and these are circular lenses. And what's the importance of lenses? Well, for example, you cannot read because your eyes are weak. You can actually use the help of a lens to focus your eyes so that you can see more clearly, okay? And in order to understand how a lens will focus, we have to find out, okay, how a lens will focus by using what we call a lens maker's equation. But before we do, let's look at this figure where lens can actually be traced, okay? This is a convex lens. The center of the convex lens is called the lens axis. If you shine a light from any object through the lens will focus the light at one point, and that point is called the focal point. The distance of the focal point up to the axis of the lens is called the focal length, and that's what we will find out, okay? How are we going to find it out? By using simulation again. So first, there, okay? First, we will have a lens, and then we will establish the focus of the lens using this number by adjusting this, okay? Second, we will place an object at any distance from the focus. Okay, you can place it here or here or here, any distance outside of the focus. Okay, and it will focus the image here, and it will give you two measurements. What are those two measurements? The distance of the object, which you can read from here, and the distance of the image, which you can read from the scale here. Okay, the distance of the object, or the distance of the object to the center of the lens, we call it U. The distance of the image from the lens, we call it V. in order to find the value of the focal, in this case, the focal is 4, right? We use the lens maker's equation. F is equal to U by V over U plus V. So let's try it. What is the measurement of U? 10. What is the measurement of V? 6.67. So 10 multiplied by 6.67 over 10 plus 6.67. What should be the answer here? It should be 4. Okay? So the question, yalla, calculate. What do you get? Get your calculator and calculate this one. Is it 4? Are you sure? You just guessed because you know that that's the answer? Turkey, did you calculate? Do you trust that it is 4? You should always have your calculator with you. Okay, I will calculate too. 10 by 6.67 over. Is it exactly 4? Logically, it will be 4. Yes, there. I want the answer from Ali. It is actually 4.00119976. You get the idea? It will not be exactly 4. Okay? Logically speaking, it will be 4, but it will not be perfectly 4. Why? Because no lens is perfect. Is that clear, Shabab? Now, let's continue. How are you going to do this and fill the table of equation, table number 4? I want you to measure the focal length at 10, okay, 20, and 30 centimeters. Where is the simulator? I have the simulator here. I will get the link and send it in chat, okay? The link is there in the chat. What else? I will send the link in your GC, okay? The link is there in your GC, okay? What you will do is make full screen, okay? What are the values of the focal length that we want? As I said, 10, 20, and 30 centi. So go to the simulator. You can actually zoom out, okay? And you can zoom in, and you can adjust your graph for the simulator, okay? Remember that for the angle table number 1, angles, you have to make screenshot. For the refraction, you have to make screenshot. For the reflection, total internal, you have to make screenshot. Here you have to make screenshot also. Which angle? Whichever you want, okay? Or which focal length. First, move the object away. Move the focus at 10. How do you know if you have the focus perfectly at 10? You can see F is 10, okay? F is 10, there. What else? You want to move your object behind the focus anywhere. As you can see, the image will also adjust, okay? So let's say I will put the focus at 10 and the image object at, let's say 16, okay? Don't worry about the height. We will not calculate magnification. So 16. If you zoom in, you will see if your distance is accurate. So 15.97, that means it's almost accurate. It should be acceptable. Is it 16 now? There. What is the image distance? 26.67 from here, okay? If you zoom out, okay, take a screenshot and submit this screenshot. Just one. You don't need 3, okay? What to do with this data? 16 and 26.67. Go to the data sheet, write it here, 16, 26.67, calculate the focal length.
Send the same screenshot, right, teacher?
And then send a screenshot. Any angle, 10, 20, or 30. Clear? Sorry, any focal length. Just one. Okay? What to do next? After you finish the first one, okay, go to the second one. What's the second? You want the focal, oh wait, not this one. This is the wrong window. There's another window for our simulation. There. Once you finish, okay, move this away, change the focus to 20. Okay, is that 20? It will jump to 20 anyway. Come on. Hold it at the point maybe. There, that's 20. Place the object anywhere. Okay, let's say 25. What is the image distance? Drag it and you will see that it's at 100. Complete the table. Okay, complete the table. And once you've completed the table, done. Kalas. But you need to show only one. Just show only one screenshot from table 4. Clear? Is it clear, Shabab? Hello? Okay, good. Finally, I forgot to discuss one application, which is very nice. If we go back to total internal reflection, okay? Why? Because in total internal reflection, you have to do some calculation. You have the critical angle by experiment, and you have the critical angle real. You will do the percentage error from table 3, okay? From the critical angle. This calculation, you have to show only the substitute. What's the substitute here? Simple. We already did this calculation, remember? We know that N2 is air, so this is equal to 1 over, what is N1? Glass, okay? For example, glass is maybe 1.7, for example only, okay? So how do you calculate this? Sine theta c is equal to N2 over N1, so you will say theta c is equal to arc sine of what? 1 over 1.7, something like this, okay? The real value, put it on the table and also substitute it in your percentage error here. What about the experiment value? Go back to the table. The experiment value is, I think it was here. What was the angle that we measured, if you remember? 86 or 68. 68 divided by 2. 68 divided by 2 is 34. Okay? So in the percentage error, this will be, for example, the real one by calculation, for example only, is 37, and the experiment 34, divide by 37, multiply 100%, absolute value. That's the percentage error. Okay? That's what you will do here. Nothing else. Sources of error. Like I said, the lens and the mirror are not perfect. Okay? So how do we write it? The mirror or the lens is not perfect. So as a precaution, you have to make sure that your mirror or your lens are perfect, but actually it's impossible. So you have to get or use, typing. So if it's not perfect, make sure at least that you use good mirrors and lenses to make your measurements, okay? What else is a source of error? If the glass is not pure. If the glass is not pure, the refraction that you will get is not with the real value for the index of refraction of glass, okay? So you must have, or you must use, pure glass for this experiment. That's why the glasses that we use for the experiment is actually very expensive, okay? In the lab, the glasses are expensive, so we use a cheaper version, which is acrylic, and it's easier to make pure acrylic than pure glass, okay? What else is a source of error? If we go back to some of the images, okay, let's take this image and let us make this image bigger. You will see that the light, which one? The white one here. The light is actually not thin. It is several degrees thick. How many? Maybe 2 or 3 degrees thick, okay? What's the effect if the line is too fat, as they say? You can see it in the error. The light rays are not thin, or they are, you can say, too fat or too big, okay? What's the effect? The angles are not accurate. So what's the precaution? You have to read the angle at the center of the light rays. So here in this image, you can see that I am reading the angle. Let me make a drawing in white, or maybe in, well, we can use white. You can see that I'm reading the angle at the center of the light, not at the edge, okay? So that your angles are accurate. You can even write in the source of error, it is hard to read the angle accurately. So what is accurately? What is the technique to read the angle accurately? You must read the angle carefully. Just you have to do it carefully, okay? Any other source of error that you can imagine, Shabab? I think that's more than enough, okay? You have to answer the questions at the end of the report. The answer for question number 1, you will see it in table 1A, okay? Go back to table 1A. Theta I and theta I prime, what's the relationship between them? Is it bigger, lesser, equal? I don't know. Well, I know, but I will not tell you. In number 2, you have to go back to table 1B, okay? What's the relationship between F? The focus is not specific. Yes, the mirror is not perfect, or the lens is not perfect. The focus will not be in the same point, okay? That's a source of error. That's why you have to make use of good mirrors or good lenses. So again, in question number 2, relationship between F and R. What's the relationship? It is there in table 2, okay? Table number 3, oh, this one, I love this question. What is the radius of curvature of a plane mirror? Anyone want to answer this question? No, don't answer number 2. Don't put the answers in the chat. I don't want anyone just copy the answer from the chat. Tell me question number 3. This is a trick question. If it is a plane mirror, does it have a radius? And what is the radius of curvature of a plane mirror? I want you to realize how physics is so much interesting on a universal level, okay? What is the radius of a plane mirror? Anyone can answer this for me? Without Google. Yes, Wasam?
Yes, teacher. We take the angle and multiply by over 180.
By 180. So what's
Yes,
the answer then?
Then will comes. No, teacher. Yes, with radius unit.
Okay, what does a plane mirror look like? A line. That's the plane mirror, okay? The light will shine here and it will bounce here. This is the normal. That's theta 1. That's theta reflected. The question, what is the radius of this mirror, the red mirror, the red line? What's the radius? Is there? Anyone? Don't go to Google. You will be cheating if you go to Google. Don't worry, I'll give you the answer, but I want you to think about it before I dismiss everybody at 11:30. So tell me, what's the radius of the plane mirror? Any idea? You can only give me 2 answers. 90? No, 90 is an angle, not a radius, unless you say 90 centimeters. The only answers you can give me are 2. Okay? 5? La. Even that one is worse. There is no number that you can give me. Okay, let me show you. I have it here in the figure. Okay? I need you to imagine carefully. Let's go to the notes. I have one note prepared for this. Okay. Imagine that you are at the Earth. Well, you don't have to imagine. We are at the Earth, right? We are somewhere near the equator. That means the side of the Earth. What's the shape of the Earth? Is it square? Shabab, what's the shape of the Earth? Anyone? It's round, right?
Yes.
It is round, like circle, but not perfectly circle, but it is somewhere round. So basically, we know that the Earth has radius. Yes or no? The Earth has a radius. Okay? Yes or no? Yes, it has a radius, definitely, because it's round. Now, I want you to go to the desert or just look outside the window. Can you see the radius of the Earth? Can you see the curvature of the Earth? Or do you see flat? So outside, do you see curve or you see flat? Without the mountain and without the jebel, you see flat, right? Why is that? We know that the Earth is round, but we see flat because we are very close and we are very small compared to the Earth, okay? So if we zoom into this Earth in my drawing, you see I highlight one area, okay? In the highlighted area, I will draw a straight line. That's a straight line, obviously. I will bring my straight line close to the highlighted area, okay? Now, I can tell you that I have two drawings. One is a straight line and one is a curve. Yes or no? Yes or no? Okay, yes. The straight line is a plane mirror. The radius of the curve of the Earth is a curved mirror. If I zoom in, what do I get with these two lines? Can you see? Oof, 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 oof. Can you see, Shabab? What do I get with these two lines? Okay, let me just adjust this line just a little bit. You will see that the Earth, okay, 1 second, just some small adjustments. There, okay. You will see that in your point of view, you see a space between them. Of course, there's a space between them. In your point of view, you see the land is flat, Sahara, okay, the desert. You see it as flat because we are very close to the surface, number one, and that we are very small compared to the surface of the Earth. That's why we see it as flat, right? Look at the football field. Can you see the curve in the football field? No, it is flat. Would you like to play in a football field where it's a curve? No, because the ball will go by itself, right? So it's the same with the plane mirror. The plane mirror here, okay, it looks plain. Why? Because you can see it as a small. But actually, if you zoom away from the plane mirror, it is actually possible that, let me make a drawing, the plane mirror is part of a very huge circle, like this, okay? You can see now what I mean. Look at the circle of the Earth. If we zoom in, you can see that it's actually made up of small straight lines. So it's actually made up of small straight lines, okay? And because you are very close to the surface, you see it as flat. But if you zoom out, it's actually part of a very huge circle. So a plane mirror is flat on that part, but you can never be sure that it's flat if you extend this mirror completely up to infinity. So that is the answer to the question. The plane mirror has a curve, and the curve or the radius of curvature of a plane mirror, it's actually infinite or infinity, okay? It can never be perfectly flat. Why? You can only see part of the mirror. You see it as a straight line or a flat surface, just like the Earth. Go outside and you see the Earth is flat, but in reality, go to space and you will see that the Earth is round. That's the answer to that question. Why the curve of a plane mirror is infinite. Any questions, Shabab? Now, for question number 4, you will see the answer not in table 3, you will actually see it in theory. Okay, in question number 4, you will see the answer in theory. Let me go to that part. The answer for question number 4 is here. Okay, that's our experiment today. You will submit it on paper next week. The screenshot, you have to print it if you can. Okay, the screenshot for what? Let me show you the screenshot you need to print. Screenshot for this. That's number 1.
Your
Screenshot
teacher
for,
or another one, or if I do
no,
it?
you have to make your own measurement. Okay, screenshot for refraction. What's refraction? This one here. Okay, when you make this screenshot, you must have the degree scale. Okay, just let me move the degree scale in the right place. So put the normal. Degree scale is 0 with the normal, 90 with the gazas. Okay, so you need to make screenshot for this. You can take 2 screenshots and put it in one paper. You don't have to print it big. I just need a small print. Okay, what else? You need to take screenshot of your total internal reflection, like this. Okay, now in your total internal reflection, Shabab, you don't need to make the angle, but if you make the angle, it's much better for you. Okay, you can print and then make the angle with a normal degree scale if you still have it. What else? The last screenshot you will make is this one. Okay, at which focal length? Whichever. You can choose the focal length of 10, 20, or 30, whichever you like. Just make one screenshot. Okay, submit the report by paper next week in GIC lab. Any questions? Okay, for me, I have questions for you. Are you present or absent?
Now 3 screenshots with the 3 from the beginning for the angle.
Again,
50 and 45.
Abdurrahman, I cannot hear you. You have to speak you have to speak more clearly. Abdurrahman.
Doctor, I said from the beginning with the first.
What do you mean? You want me to repeat everything from the beginning?
No. I mean the first schedule where the angles is 30 and 45 and 60. Do you want?
You want to repeat that one?
Screenshot?
No. Just one angle. Sorry, just one focal length. Okay. You can take from 10, from 20, or from 30. Bas. You just need to show, Shabab. You just need to show what? The focal length with the distance. Okay, what's the distance here? 25. What's the distance here? 16.7 maybe. That's it. You just need to show this, okay? Something like this. Now, don't worry about this text. I don't care about this text because I can read from the mastarah here and from here, okay? Wallahi, I don't know if we can switch off the text. I wish we could. No, there is no way to remove the text. Okay, any questions? If there's no more questions, then let me check the attendance for everybody. I have 14 students. That means the same number. Faisal 256, Majud? Faisal 256? It's not here. Ahmed 825? Ahmed 825? Okay, I have the 14 students with me. Yalla Shabab, I will see you next week in JIC. Keep safe, okay? Keep safe, and if you have scheduled for vaccine, you still have to wear your mask. That's our lesson for this week. You can leave now once you have no more questions. Okay, Ali, thank you. Yes.
This experiment not to last in the final exam. Yes.